any problem is there, I'll repeat the content at any point of time. So with this,
Yeah,
shall I
sure,
start,
sure,
sir?
sir. Yeah. Heavy rain here also. I just drenched myself and came.
Yeah,
Just reached on time. Yeah. Let's go ahead. Let's hope if there's any break, please wait. Please don't log off. Please don't go away. We will sort out the
yeah,
issue within 1 or 2 minutes. There may be issues
right.
here in MNIT also, so don't worry. The lectures will continue, but in case there is any issue, please wait. We will restart and resume. Right. So over
Yes.
to Dr. Mustafa.
Yeah, thank you so much. Yeah. So I hope I'm audible and my screen is visible. Shared screen is visible, whiteboard, right? Can anyone confirm?
Probability and statistics in quantum computing. Yes, it's visible. Slide is visible.
Thank you. So this subject, probability and statistics, if I talk a little bit, why things are coming in the right side, a lot of things. Let me mark questions. Okay. So the subject itself, like probability and statistics, although we are studying it from our childhood, like school days, but there are lots of theories, even under uncertainty, we do not know, do not tell a concrete solution. So there are lots of decision science associated with probability theory, statistical inference, and there are master's, PhD level courses on these things. But I am just covering very basic things because it's a QT-00 course. So very basic stuff in probability and statistics, which exactly they have some connections. I'll try how they are connected to quantum computing, especially quantum technology, various aspects. And a detailed note I already shared to Professor Pillai sir, as well as if you want some more advanced material, such as the estimation theory, like likelihood functions, various hypothesis testings, and other details. That note also I do have, so I can share with the course committee. But for now, it's very basic stuff. So with this, let us start probability and statistics. And I'll share the book material, like reference books like Day-4 or the Anesthesis Populis. So there are certain good books on these. Populis books is one of the best books in probability and statistics, or you can choose any other book. So I'll give all the reference details later on. So let's start. So let's start with the the day one, what we started on quantum physics, especially the quantum postulates, right? And we'll then go to the basic statistics, basics probability theory as per the syllabus for 1 hour, and then I'll connect the how the probability is related to the quantum computing part in the second half. Okay. So quantum postulates part, what we have seen. So there are certain things, first of all. So I'm just giving you a summary, and that is related. Yesterday and day before yesterday, we connected everything to linear algebra, right? And today we'll be connecting everything to probability theory. So what we have learned from the previous class is what is superposition, right? Superposition theorem we have learned, and how we have defined it with simple linear algebra, like any vector, right, that belongs to certain vector space capital V, right? So any scalar combination of this X and another scalar combination of another vector, say Y, right? So if X and Y belongs to the vector space V with the set V, and if there are two scalar quantities alpha and beta, they belongs to some scalar field, set of scalar numbers, right? F. Then this combination, if it is some another vector Z, which is alpha amount of this vector X and beta amount of this vector Y, then G vector should also belongs to the set capital V from vector space definitions, right? And this combination, basically linear combination, alpha times X vector plus beta times the Y vector, this is called the linear combination of vectors, also known as the superpositions phenomena, right? Superposition of vectors. But there are some additional conditions I told, alpha and beta, right? And that I'll talk today, especially about alpha and beta from the probability theory, right? So let's revisit again quantum postulates, right? So what we have learned that the first of all, the configuration. So there will be experts who will be teaching the quantum physics in detail. So don't worry. So these things will be discussed in much detail, and why, what are the underlying physics behind it, or the experimental stuff, such as the these Garchlet experiment and all. So I'm not going to that direction. So that will be covered by other experts. I'll just stick to the probability and statistics part, and I'll just try to connect this with the quantum physics and computing part. So first is the configuration of any physical phenomenon, especially configuration of particles, right? That will be described with some wave function xi x comma t. Fine. So very simple. This is how, like, the quantum postulates, how it is designed, right, or how it is proposed in very like over decades in the last century, right? So this is one. And exactly that we learned the equivalent representation is ket psi, right? Which is basically a vector, a column vector. In algebra, we have learned it's a column vector and normalized. Okay. This norm of this vector equals to 1. Right. So this is one fundamental requirement when you will design these wave functions to a quantum computer. So you have to convert this to a vector, suitable vector form, right? Suppose you have a function like this, and you want to encode these functions to a quantum computer. So you have to discretize it, right? In 2 power n, if you want to encode in n qubits, 2 power n points, right? 2 to the power n number of points. Then there will be strategy how you can encode these functional values. So if you store all these values as a vector, right? Say the vector is v, then you normalize this vector, right? You normalize this vector as ket v, and then you put it to a quantum computer using certain quantum encoding techniques, right? So this is how the physics is related to the computing part. So this is the first quantum postulate. Then the second one is related with the the extension of one, you can say, or the second, you can say, that chi square x dx is the probability, right? It is the probability of finding the particle, in x and x plus dx, this region. What do I mean? If a particle distribution looks like this, right? Suppose this is your x-axis space, and this is your psi x. Suppose this is represented in terms of the variable x, or space. X is space, basically space variable. We could also think with respect to time and space, okay, or any variable x, right? And what is the probability of this particular thing, right? This particular wave function between x and x plus dx region is this area, right? So first of all, you have to take the square of this. If it is xi of x, then you have to do xi square of x, right? Then times dx, this region, right? Dx, that will give you the probability. So equivalently, what we can see, although I am not defining each and every what is like random variable and etc. I'll come slowly bit, but for now, let us connect. So if there are there is a random variable x, right? And the associated probability mass function px, or this is called PMF, right? And this is f of x, say this is your PDA, probability density functions, right? Probability density function. So what we have seen, that expectation of the mean, right? Especially the expectation of any event, right? Or in this particular case, it's a wave functions, right? So we know that it is f of x, right? X f of x dx, right? This is what is the expectation we know, right? Expectation of the random variable x, right? And if it is a continuous function, so integration of x fx dx between x and x plus dx region, right? Or you can say x1 to x2, whatever it is. So this is how we find the expectation of finding an event, right? Which is basically following a PDF times the random variable, right? Between the point x and dx. And if it is a like a discrete event, what we do, summation of random variable x times the probability mass function p of x, right? This is the expectation of that random variable x times the probability mass function p of x, right? This is just simple definition that we normally learned in our schools. I'll repeat again what is random variable, because it's a 0-0 course, so you do not need to worry about this basic thing. So I'll define each and everything slowly, and I'll give example. But for now, if we compare the quantum physics versus these things, it's basically these wave functions looks like the probability density functions, right? Where the particle or how the particle is distributed, right, within certain region. And if you want to get the probability, it's basically the square of that times dx, right? So now, I mean, it's not the expectation, first of all, but how I'm just relating how the things are calculated, right? Now, the third is we also learned about observable, right? Like if there is an operator a hat that acts on the wave function, say psi of a of x, and it gives the eigenvalue, right, a times the same wave function psi of x, right, this way. So basically for every wave function, there is a corresponding operator which acts on the wave functions and return a value, right, which is the eigenvalue of that operator, of that particular operator a, right? And this is your desired quantity, right? And yesterday we have seen a little bit on the eigenvalue problem and the eigenvalue decomposition thing. So that is fundamental to quantum mechanics, this particular equation. So how you should design an operator such that you get a particular eigenvalue of that operator, which corresponding to your desired quantity, maybe momentum, positions, energy, frequency, etc. Right? So this is related to that. Then we learned about the superpositions phenomena, right? So if if psi1 x and psi2 x, these are two valid quantum states, are valid quantum state or wave function, you can say, are two valid wave function. Here I am saying quantum states, right? So typically these are function, I should say, because if I put the Ket notation, then it will be your quantum states. Now I'm saying it's a wave function. Wave functions. If these are two valid wave functions, right, then I can always prepare another wave function, which is a superposition of this or linear combination of these two wave functions, alpha amount of psi1x plus beta amount of psi2x, right? Provided there are certain conditions on alpha and beta. So basically, this is equivalent to your Ket of psi x, that is a vectorized notation, right? Alpha times your, say this is your psi1 x Ket plus beta times your psi2 x Ket, right? This is what we do, provided alpha square plus beta square equals to 1, right? So that means if there are two boxes, for example, box 1 and there is another box 2, right? And if I distribute certain balls, right, in box 1 and box 2, so that means what is the, suppose I can keep a ball, say a ball either in box 1 or in box 2. So suppose whatever way or how many times. So suppose the probability here to get this ball is P1 out of 100 times. And the probability of getting this ball in box 2 out of 100 times is P2. But on an average, whatever, how many experiments I do, so altogether the total probability will be P1 plus P2 equals to 1, because otherwise the ball is disappeared. That is not the situations, right? So the total probability should be equals to 1. Now, there is, we have also learned the thing that is, so this is, so generalization of this is, I can generalize this. So that is equals to psi of x if it is discretized now. So earlier I was writing the continuous part. Now, if these are discrete wave functions, then I can always write as CA. So phi of, so these are individual wave functions, and I am taking a basically superposition linear combinations with coefficients, say CA over A times, right? So this is the generalized versions. Now, This psi A in quantum computing, we have seen it is as Ket0, Ket1, or Ket00. So these are like non-computational basis, right? So you could write it as alpha Ket0 plus beta Ket1, right? For like 0 and 1 qubit settings, or more qubit, you can take like alpha, beta, gamma, delta, or more number of coefficients, right? So these are more generalized representations of quantum superpositions, right? Now the last one is so even if I represent in this way, right? So what is the probability of the of a particular wave function in a particular basis I? So probability of the wave functions getting in the particular basis, say I. What is the probability of that? It's basically C of I square, right? From this equation, if A equals to I, for example, here in this case, right? Ci square. And how can I get this Ci? I can get this Ci as inner product of, I have to do the projection of the operator in the measurement basis, right? That means phi of I, if it is the measurement basis, right? Inner product with psi is my wave functions, right? Mod of that. So this is in continuous space, this is integration of dx phi I star psi x, right? Between say two particular region minus infinity to infinity if you give. So this is like how, so this is, I also explained this in linear algebra as well. Like if this is your wave function psi, ket psi, say for example, and it has alpha Ket0 plus beta Ket1 representation, right? So how can I get the alpha and beta? So if this is my Ket0 and if this is my Ket1, you can do inner product between this 0 and psi, you will be getting alpha. You can do inner product between 1 and psi, you can get beta. And if you square them, basically that will give you the probability alpha square and beta square, right? And total probability sum alpha square plus beta square equals to 1 from quantum postulate 1, right? Now, there is one more quantum postulate we need to understand, that is the measurement, quantum measurement, right? And this is the the most controversial part in quantum computing, because there are so many interpretation of measurement, like the Copenhagen interpretations, and there are rank one measurements. So there are POVM, lots of literature. In fact, there is course on quantum measurement. Okay, so I'm not going detail, but if you do the measurement, so you collapse the state. For example, if I do measure of this particular wave quantum state in the basis 0, so I collapse it and I get the probability alpha square. But that particular time, so this state is already collapsed. So normally, if there is an operator A, right, which has an eigenvalue little a, right, then we get the, if it is a measurement operator in this particular case. So let me write in a different way. If I have a measurement operator A, right, and if I apply the measurement operator on the wave function psi of x, I should get AM psi of x, right? So this is my measured quantity, and basically I get that particular basis, eigenbasis, right? Now let me tell you certain facts here, because you might be confused with certain things. So let me tell you that part first. So yesterday we have seen certain things, right? The Pauli X operator looks like this: 0, 1, 1, 0. Pauli Y operator. So these are various quantum gates, right? 0, minus I, 0. These are rotation gates, basically rotation matrices in the Bloch sphere. And this is 1, minus 1, 0, 0, right? Now, typically, the beauty of quantum superposition, like there is a lot of important part or important implications of quantum superpositions, and one of them is, so implication of superpositions. Let's start this part. Right. So what superposition theorem tells us is that psi of x I can represent as, say, C of I coefficient times certain of certain basis. Say this way, I'm writing in the vectorized notation. So ket psi x or ket psi is a superpositions of certain basis times the coefficients, right? So, so this is what superposition theorem tells about. Now, suppose I can represent the wave function psi of x in many ways, right? So for example, if I write it in this way, 1 by square root 2 pi integration for the continuous, if I take it continuous, right? If I take it vectorized, I can take summation, right? Integration dk psi tilde k e to the power I kx, right? So what I do, there is a wave function. I do not know how it looks like or how I can represent in a better way, right? Because it's highly uncertain. It can simultaneously stay at many positions, right? So it's very difficult to basically localized in X. For example, this is X and psi X. This is very hard to localize, right? But if I can write this wave function as a sum of what? Sum of plane waves. Sum of plane waves, that is e to the power I kx. I can write from the Euler's expression cos kx plus I sin kx. Is so in the second day we have seen this in the complex number representation. E to the power I kx equals to cos kx plus I sin kx, right? So that means I can represent as a linear superpositions of this basis becomes my exponential basis or the plane of some waves, right? This is exactly what is we call as a Fourier transform representation or Fourier. If it is a periodic case, we can write it as a Fourier series representation, right? So any periodic function we can represent as a sum of certain coefficient times say ai times cos theta plus bi times sin theta this way, right? This is exactly what Fourier series tells. But if it is non-periodic case, you can always write in the integral form, right? That you can represent that same function in this form like some psi tilde k e to the power I kx like sum of plane waves. That means it is difficult to visualize this. Can I write it as a sum of plane waves? Because plane waves, yesterday we have seen like there are two wave packets. Like one is the Gaussian wave packets we have seen, like which is localized in a space x. This is localized in x, psi of x, but uncertain in p momentum, right? It is good in x, localized in x, but uncertain in p. But if it is a this is a Gaussian wave packets, but if it is a plane wave packets, so it looks like this, like so it looks like this. Say for example, like this one. Now, of course, it is not localized in x. It is not localized in x, but I have all the information about lambda wavelength, right? Wavelength is known here, right? If the wavelength is known, what are the other things I know by de Broglie's like the Broglie formula? We know that if I know the lambda, then lambda equals to your h by momentum, right? H by p, right? So p equals to you can write h by lambda. So if delta lambda is very less, that uncertainty of lambda is very less for the plane waves. That means uncertainty of the p momentum is very also less, right? So it is also related with the wave number k. You can also write wave number k defined as 2 pi by lambda, right? So p definition of p is h by lambda. So also you can write p equals to just comparing these two equation, you can write as h bar k, right? So where h bar equals to h by Planck constant by 2 pi, right? So this is the expression of momentum. So once you are now certain about the momentum of the particle, right? Hence, you are very uncertain about the wave function, but you can express this wave function with some certain known momentum plane wave with definite momentum functions, right? So once you know certain definite momentum functions, can you create can you create some basis functions, orthonormal basis functions, where you have some definite knowledge of momentum, right? So now in computer science, we have seen, okay, we are taking Ket0, Ket1. Now how it is related, right? So my digital screen is creating again some issue. Let me take a new page, maybe. Let me try with this. Right. So yesterday we have seen that the operator Z is important. The Z operator 1, 0, 0, 1. Now any vector, right? The quantum state vector is just a vector. It's a simply normalized vector, right? So you can represent this vector with alpha times Ket0 plus beta times Ket1. That's fine, because 0 and 1 in digital computer, these are some computational basis states and very easy to define. But you can also represent as alpha 1 times, say, E1 plus beta 1 times E2. What I mean to say, suppose you have a three-dimensional space like this, a representation, right? And this is actually, this is called a Bloch sphere. So this is your Ket0 and this is your Ket1, right? And suppose this is your wave function psi, Ket psi. You can represent this Ket psi with the basis 0 and 1, fine. That is this one. Now I say this is my basis system. This is a very different basis system, this one. And I say that these are to my orthonormal basis E1 and E2. Suppose these are eigenbases, right? In this reference system, this one, this particular reference system, right? Now you can see, you can better probably describe this wave function maybe on these wave functions, because it's a simply probably addition of this some linear algebraic addition of this E1 and E2, right? So sometimes it is not always the case that you need always 0 and 1 for base bus. Computationally, this is easy, right? But in physics, you may always go for a better reference system where you can better represent your wave function, maybe momentum, maybe positions, maybe computational basis, or some other basis states, right? Achha, somebody asked me, can you repeat? Okay, let me repeat again. So you have a quantum state, right? This quantum state. Now, how we learn to represent a quantum state? Alpha times Ket0 plus beta times Ket1, right? It's a simply vector. It's a vector, R vector. Now, how many ways you can represent this vector? This is a reference system, right? X and Y, orthonormal reference system, 90 degree, right? This is some amount of X, alpha amount of X plus beta amount of Y, right? If there is another reference system, suppose, right, in principal component analysis, you have seen that those who have used the machine learning literature, that if you have a principal component and if you have a reference system, something like this, suppose this is your first eigenbasis E1 and this is your second eigenbasis E2, where your most of the data is correlated, right? So you may find a reference system like this, not this XY system, but this is a different system and there is also 90 degree. That means they are orthonormal to each other. Now you have a information, say Ket x here, Ket psi here. You can also represent this Ket psi as some other coefficient, say gamma times E1 plus delta times E2, right? You can always express this way as well, right? Similarly, you have seen that if there is a like radar, for example, suppose you are sending a signal from this place, suppose there is a ocean and there is a mountain, right? So suppose there are two mountains, okay? And you send a signal and you get the return back. Now, if there are two mountain with some distance apart, if there was a single mountain, you can get a single peaks in your spectrum, right? After Fourier transform. But if there is a like in time domain, what will it look like? This one, like this way, right? Now you have to detect this peak. So sometimes you are not sure why this change is coming in the envelope. Is it surely there are two mountains, or this is due to noise or something else, cloud or something else? So this is a critical detection problem in radar. Okay, so that's why we do Fourier transform, right? So there are like advanced algorithms like music, spirits and all. I'm not going to that direction, but simply we go for a frequency domain analysis and we see two peaks in the frequency domain, frequency versus the energy plot, energy versus the frequency plot, right? So that means now in frequency domain, it is easy to represent this same wave function psi of x, right? So that time you even do not need to represent your wave function in alpha times k0 plus beta times k1, because now you have a better representation, say a times your Fourier basis 1 plus b times your Fourier basis 2. That means you need to find out which is the best basis representation of my wave functions. In chemistry, there are STO bases, right? In various chemical configuration of molecules, like if there is a benzene molecule, right? So what is the best basis set to represent that, right? Or if it is like say simply CO2, right? So or simple carbon, right, chain, like say for example CH4, right? So so there are various basis system how to represent the wave function of such molecules, right? So this is extremely important, just not quantum computing, but we need to understand which is the best representation system of my wave function. Maybe my computer is not enough to directly find out this basis, but that is the limitation of your computing technology, not the physics. Okay. Uh, okay. Now, any literature when you go to from physics or engineering to quantum computing part, we do not have specialized device to prepare this Fourier basis or eigen basis. What we have a simple thing where we can create ground state, excited state, and call this is gate 0, this is gate 1, right? Or certain ion trap technology, certain atoms for gate 0, certain ions for gate 1, or in a polarized system, okay, this is vertical polarization gate 0, this is horizontal polarizations of photon, this is gate 1, right? So various technology we are able to define Ket0 and Ket1 informations, right? And that's why you will always see people are calling JADE gate as a measurement basis gate. JADE gate as a measurement basis gate. Why not X gate? Why not Y gate? Why we are using JADE gate as a measurement basis gate? Why we always prefer to use JADE gate, right? Now, let's start with the counter example, then we'll go for the actual example. Okay. If I use X gate, suppose, so what is my X gate? Poly X gate, sigma X or X. This is equivalent as X gate, okay? Not gate or poly X gate. It looks like this one. And I apply say 0 here, right? So immediately, so 0 means gate 0 means 1 0. Okay, it's a vector. Immediately what I get 1 0 1, right? So I apply 0 and there is what I get is 0 to 1. Immediate changes, right? So means there is a bit flip, right? Bit flip, erroneous, right? So my entire vector changes. That means if I was sitting here, my information should give me Ket1, for example. But once I apply X here, I immediately get here my information in Ket0, right? It is changing my information totally if I apply the X gate. Now if I similarly, if I apply Hadamard gate, right? My information is at gate 0, and if I apply Hadamard gate is what? Hadamard gate is your 1 1 1 minus 1 and normalized by 1 by square root 2, right? If I apply in the class, what I get is if you do the simple multiplication, you will get 0 plus 1, superposition of 0 and 1 by square root 2 normalized, right? That means if I am here, I am supposed to get my information here at Ket1 or Ket0, for example, right? Ket0. Once I apply the Hadamard gate, I reach to this superposition plane. I reach here. This is called plus state, right? This is called plus state. In fact, this is the eigenbasis. I'm not going in detail. This is Fourier basis or eigenbasis in quantum computing framework. Sometime when we'll cover the quantum Fourier transform, we'll come back this state again and again. Okay, but for now. But if I use the Z gate, what I get? If there is 0, right? And if I apply the Z gate here, what is the definition of Z gate? 1, 0, 0, minus 1. Let's see what is the output. Output is 1, 0, 0, minus 1, right? Times 1, 0. So if you just simply multiply it, 1 times 1 is 1, 0, 0 is 0. So this is 0, right? So what this equation tells, this is exactly Z times KT0 equals to 1 times KT0, right? And this is exactly Ax equals to lambda x equation, right? Your lambda equals to 1. That means I have found out, or I have forcefully created computational basis as a measurement basis. Measurement basis. In fact, this is the eigenbasis with the eigenvalue 1. Eigenvalue equals to 1, right? So if I apply a Z operator on a information, it does not impact the information. It does not change the information. But in fact, it gives the eigenvalue equals to 1, right? With the same eigenbasis. So there is a question in that sphere where Z axis is. Okay. There is no Z axis thing. That is the computational basis representation. The in this picture there is no x-axis, y-axis, z-axis. This is called the block sphere representation. So there will be sessions will be taken by experts. Please bear with us. Like there will be special sessions on this by somebody. What is block sphere? What is Q sphere? How to represent quantum information, programming, everything will be there. I'm not covering because I just respect all their sessions. So I'm keeping these things as curiosity. Okay. Okay. Now, what is the physical significance of G gate? Now, G gate is an operator. And if you apply this operator on the quantum state, you get the same state with the eigenvalue 1, right? Now, if I apply the measurement multiple times, and I can check how many times I can get KT0 by applying that measurement operator, right? Suppose I perform n times quantum experiment, the same quantum experiment I repeat for n times, which is called shorts in quantum computing. When you will be doing the programming, this is called shorts. So if you do m number of sorts, say, right, m number of sorts, and suppose you get, say, n1 number of 0, n1 number of 0 computational basis, then we say the probability of getting the wave function in the 0 basis equals to n1 by m. Exactly. In fact, you will see when if I start with a KT0 state, I apply a Hadamard gate, right? So my state is 0 plus 1 by square root 2. So let's take two 0 state and apply 2 Hadamard, right? So at the output, here and here, it's a composite system now, right? So here also 1 by square root 2, 0, 0, right? 0, 1. So eventually this, I should get 0, 0, 0, 1, 1, 0, and 1, 1 with all equal probability 1/4 theoretically, right? Practically, it may be slightly different, right? Due to noise. But actually what I should get, my computational basis 0, 0, 0, 1, 1, 0, and 1, 1. And I should get the function or histogram, right? And all these values are 1/4, 1/4, 1/4, 1/4. Now, if you simply apply a CX gate here, control X gate here, I'm not detailing things, but I'm giving you an example. This is called the Bell state circuit. You will see immediately it creates an entanglement between these two states 0 and 0, right? Between the qubit, first qubit and the second qubit. And your overall state become 1 by square root 2, or it's possibly half, basically. You need to check once. 0, 0 and 1, 1. Okay, because of this entangled gate, right? And immediately we'll see that only because of the entanglement, this 0, 0 state and 1, 1 state are giving probability of half, whereas these two state like 0, 1 and 1, 0 has the 0 probability theoretically. In practically, we'll see some values here and some less value than half, right? Due to quantum hardware noise. Now, this is exactly how we created interference by using this C0 gate, CX gate, right? And by creating a Bell state or entangled state, by just we can manipulate the probability from this histogram to this histogram. So now, so that means there are lots of things, lots of probability literature that we can apply our knowledge of probability statistics, how we can design some algorithms. And if we know, okay, this is my solution state or this is my solution state, how can I design certain mathematical algorithms such that the probability is maximized for this particular state, and for all other state, I can minimize the probability. That's the overall goal of quantum computing. With this, I am taking a 5-6 minutes break, and then I'll come back with the quantum interference and sessions on probability. If you have any question, please put it here. So I'm slightly deviating certain things. I have provided the notes on basic probability statistics, those who are new. Due to limitation of time, I'll not cover every definitions or other things because that is too boring, but that is important as well, right? So today I'll define random variable, continuous random variable, probability density function, central limit theorem, and some basics of hypothesis testings and their applications in quantum computing. CX gate is applied here in the bottom qubit with the control in the first qubit. It is a controlled gate. So keeping the first qubit as a control and applying it on the second one, right? So this is the way how it is applied. So there is something called a target qubit. There is something called a controlled qubit. So, okay, there are various types of circuit designing phenomena, ancilla qubit, target qubit, control qubit, and I'm not covering this thing. This will be covered in future courses. So I'm keeping it curiosity for now. Okay, this one I have taken as first qubit and this one as a second qubit. This is the first qubit and this is the second qubit. Right? So qubits are placed in the left side and gates are applied in front of the qubit. In this way, circuit is designed. Superposition is linear combination of basis vectors, exactly. Well, of course, but with a certain, if it is a quantum superposition, then it should obey the probability law, like sum of the square of the coefficient for superposition equals to 1. So the way I am covering things is probably not, it won't be the way how physicists will be teaching you. They will give you more details, experimentational proof and everything. I'm sorry because not having much knowledge in the physics side, but I'm trying to take it with a very different way, my way, own way to explain things in the mathematical way that is how it is possible. So it's an experiment from my side as well. So if you feel something as a feedback or like if you find anything error or suggestions, you are feel free to put here. Explain how CX gates will work. I can explain, but I'm pausing this question. I will take it later in maybe QT-01 or other courses. Or probably somebody will take in this course. So there is quantum computing sessions. You may ask these questions there as well. So typically it's basically a matrix. CX gate is a matrix, looks like this 1 0 0 0 0, 1, 0, 0. Now 0, 0, 0, 1 and 0, 0, 1, 0. So if you see in the first part, it's like identity matrix, and if you see in the second part, it's a X matrix like poly X gate. So the CX gate, it is defined as the 0, 0 outer product tensor product with identity matrix plus 1, 1 tensor product multiplied with X gate. This is the definition. So now it's a complicated thing. I could explain, but I'm pausing it here. We'll discuss sometimes later on. Yes, this is a extremely good question. Why K0 and K1 are orthonormal, but they are separated by an angle of 180 in the sphere representation? Okay. Okay, somebody will explain this. Just I'm telling you that in block sphere, opposite pole represents 90 orthogonality. Okay. In normal sphere, this point and that point is 90, right? But in block sphere, the opposite polarity means orthonormality. By this screen. Am I audible? Can someone confirm?
Audible, sir.
Yeah, thank you. My screen
You
suddenly
you are audible. You are audible.
sharing was suddenly off. So in blosphere, actually, you will see later on that the opposite polarity means 90. Okay, explanation may be given by other experts. So skipping this part. Okay, so I'll briefly cover quantum interference in terms of probability, and then we'll go to some basic statistics, right? So let's start. So what quantum mechanics tells us is that using the superpositions theorem, right? That is everything, entanglement, interference, I'm telling you, everything is coming from the superposition principle. And this is extremely powerful. Superpositions theorem. In fact, you can connect Fourier transform, wavelet transform, anything to superpositions theorem. Yeah, if you simply represent things in terms of vectors, linear yeah, compositions of vectors. Now, what this theorem tells us is that suppose I can represent a wave function psi of x. I'm removing the time part, time variable. It's simply a function of space, or we can write as psi xt, for example, at phi 1 x e to the power minus omega 1 t. This is a sum of two plane waves, for example, psi 1x e to the power minus omega 1 t, and psi 2x e to the power minus I omega 2 t, right? Now, the probability of x comma t is psi of x comma t square whole square, right? And this is how we write it. If it is a complex quantity, right? Complex quantity, then we can write it as psi star psi x, right? So it's a function of x comma t is a function of x comma t this way. Immediately, we can write it as phi 1x e to the power I 1x. So I imaginary part of minus I complex conjugation will be I, right? Star, yeah, star of this to the power, this will be I, right? So then plus phi 2x e to the power I omega 2t, right? Into multiplications with phi 1x e to the power minus omega 1t plus phi 2x e to the power minus omega 2t, right? Either you can take I or j, so any one, right? So if I simply multiply these two parts, like this with this, then this with this with this, and this with this, what are the terms I'll be getting? First one will be psi 1 square, psi 1x square, right? And the last term will be phi 2x square, right? These are the two terms. I have two additional, these are two terms, and I will have additional two terms because of this first one is e to the power omega 1x, and e to the power minus omega 1x will cancel each other. Similarly, in the fourth part will cancel each other. So you will have phi 2x square. But the intermediate two terms, these terms and these terms will be phi 1 star phi 2 e to the power I omega 1 minus omega 2t plus phi 2 star phi 1 e to the power minus I omega 1 minus omega 2 t, right? So now you can easily check that in fact this is the probability of getting this particular wave function, right? This is suppose probability 1 and this is suppose probability 2, right? Probability of the wave function, that is P2, and the total probability equals to P1 plus P2 plus something else, right? Something else. And that something else is only possible because I have taken two wave functions having two different frequencies, W1 and W2. And that is creating these two extra part, which is not directly P1 or P2, or I cannot write P1 times P2 or square root P1 or P2. I cannot write that way, right? And that extra part is called the interference part. Interference, right? So total probability in quantum physics, you can never say that it is the individual sum of probabilities, P1 plus P2, but there is some additional term that may come into picture, and that I can only vanish if and only if these two wave functions, psi 1x and psi 2x, if they are vectors, for example, then the dot product between these two vectors is 0. That means they are orthonormal. If this is the case, then only this interference can be vanished. Unless otherwise, these extra two parts will be there in the picture, right? So this is how interference come, and this is in fact all the quantum algorithms you will be acting on this phi 1, phi 2, and phi 2, phi 1. How you should design various, how you should apply various gates in order to impact on the first qubit, on the second qubit, or some nth qubit to create the interference and all. You have to play with these probabilities, extra probability terms, right? So there is things. The first term is the exp power should be in x, where it is exp power. Okay, so if it is t, yeah, I may sometimes create mistakes. I am not following notes, I'm writing my own. So I'm sorry if there is some typos, I should rectify these things. Yeah. So this is the things called interference, and we need to play with the interference in order to like, suppose this is the initial probability mass function of certain quantum like basis states, like the computational basis states versus the probabilities. Now, how you can create out of these two, say this is my important basis, these two are important basis, and all are should be 0. So the probability should be maximized in these two cases, and for others, the probability should be minimized, right? Something like that. So that is the whole purpose of your quantum algorithms, right? You will be reading later. Now we completed 1 hour, and we'll be going to the basic probability again. Basic probability and some more applications in the quantum computing. If you have any question, please feel free to put here. today I'll ask some questions as well during the lecture. So I'll provide some questions so that you can do some homework with me as well. Let's take a 2-3 minutes break and I'll come back with the theory again. Because it will be a slightly different way. Orientation will be slightly different way. Yes. Okay, there is one question. Can you explain the significance of interference? Okay. There might be many answers. Um, okay, physicists will tell you that something like this. Suppose you have wave functions like this, and if you have another wave functions like this, so together it will give you some solution, right? Where you can see some of the region you have more amplitude and you have less amplitude, something like some of the energy of signals are concentrated in certain frequency region. So that is one answer, direct answer. That is the case of interference basically, right? But there is a different answers as well that I have given you, the probability, how you can manipulate the probability, right? So that is another part of interference. And let me give you one more answer that is from the computation part. So that is, suppose you started with many zero, right? Say 3-0, you have started a state, right? And you have applied Hadamard gate everywhere. You have created superpositions, right? So now you can say with 3 qubits, I have created 2 to the power 3, 8-dimensional space, right? I have created 8-dimensional Hilbert space. So I have, what other things I have, basis states I have, all 0 to all 1. So 8 basis states I have created, but all has the probability 1 by 8. Probability equals to 1 by 8. Now, what is good for this? It doesn't mean any solution here. You have created a bigger space with all 1 by 8 probabilities, right? If you do measurement here. So with only superpositions, you can create huge space. That means computationally, this is good, but it does not give you any good answer, right? All solutions are equally possible. That means you have created a very good computation machine with no purpose, right? That doesn't mean anything. So intelligently, what I have to do, I have to go for the solution I want. That means I have to play with this probability. I have to make this is like 1/2 and all others like less than that, for example, right? So some of the solution I have to get 0.9 probability, but others less than 0.1. If this is the case I can do, then I get some exact solution, and that is the purpose of interference. From your superposition state, it will create interference on the probabilities, and it will forward you towards the best solutions, right? That is the purpose of interference in computation, right? Okay, so now let's go to the part probability again. Okay, there are many questions. Okay, let me take one more with regard to measurement. There is measuring the outcome of superposition of waves, and measurement the collapse to one of the outcome 1 and 0. But suppose there is another different wave functions. If we measure the wave with regard to another different wave, can store of the information be increased? For example, we have energy wave representation in intellectual. We can measure the outcome, but if the energy is emotional, this is a great question, sir. If the energy is emotional, can you store more information? Okay, so maybe towards the end of we can discuss this. I won't hear you satisfactorily, but I'll try. So question is really very good. We can do with this equally likely event. Bell state does not have interference. Of course, the entanglement itself is interference, right? But how you create entanglement, right? So I mean, how you define entanglement, that's a different story. Again, like completely correlated qubits are completely correlated to distinct object, right? So that means you have created ultimate interference such that some other states are vanished totally. Only interfere part is there to between two entity or two event or two computational basis states, right? So yeah, then okay, let's start. Now let's move towards the probability and statistics. Okay, let's start with engineering context. Okay, and then we'll go to the theory. So, so all our engineering systems, right? There is inherent noise, right? And just give me 1 minute, maybe. So ideally, you have certain input to the system X, right? In engineering system, and you have a system here A, and you have a output Y, right? Uh, so if it is a telecommunication system, for example, transmit certain data, right, from your TX antenna, and you receive certain data in your receive antenna, RX antenna, right, receiver side and transmitter side, and there is a channel, right? So in a it can be wired channel or wireless channel. Suppose it is a wireless channel. So there are many uncertainties in the channel itself, that your signal, if you are transmitting a signal, it can be absorbed by trees, buildings, mountains. It can be reflected. It can be refracted. So there are lots of uncertainty factor in your signal transmission and receptions, right? That is one uncertainty part coming. Another thing, when you process your information through various hardwares, hardware 1, hardware 2, hardware 3, right? Like some circuits or some physical device, device 1, device 2, device 3, all this information X or information if you receive at Y, Y1, Y2, which is passing. But every time it passes through a device, like Y basically you get Y1. So all these devices, thermal noise, Brownian motions in their electrons, like in a more atomic scale. So that's all together basically interference. Like I transmit 1010 and I 0 corrupted due to noise, right? It's the total information is lost if you calculate the capacity and all. So basically, we have to treat equivalently when we'll be working with qubits, the ket0, and ket1, right? This is suppose transmitted in a quantum communication channel, and suppose you receive say ket0, ket0, and ket. Basically, it is right a bit.
Sir, you
To
sorry for interrupting, but your
the
voice
actual
is
hardware.
not coming properly. Uh,
Quantum. Sorry,
sir,
quantum
your voice is not coming properly.
and all these things. So related are so basically, if I can model the noise, then only I can understand how I can mitigate them, or how I can correct them, right? Sir, can you confirm now? Is it clear? Better?
Yeah, now it is okay, sir. But in between there was some break. So can you
Okay.
repeat?
Yeah, sure,
Uh,
sure. Why not?
Yeah. One part. Yeah.
Yeah, sure, sir. Yeah, thanks for letting me know. So yeah, so we are just discussing these probability and statistics in engineering context. That suppose when basically some information is transmitted, right, and it passes through certain hardware or wireless channel, and you receive certain things, say ket X, and you get ket Y, right? The quantum information, and that quantum information, whatever you get, that information is basically it always not the ideal case because of the behavior of the hardware devices, or both in the classical as well as in the quantum context, this can be noisy, right? And to analyze this noise behavior, right, on certain factor, right, uncertainty that is coming due to this physical hardware or the errors because of the various hardware issues that we'll be studying later, we need to understand various factors associated with uncertainty. That is equivalently both that is both they are both in the classical picture as well as in the quantum picture. In addition, your information, we are saying that my quantum state kx can be superposition in ket0 and ket1. That means it does not have a definite state of ket0 or ket1, but it has a superposition state of 0 and 1. That means it can simultaneously in the state 0 and simultaneously in the state 1 by the quantum nature, with probability alpha square to the state ket0 and with probability beta square with the state ket1. That means quantum information itself requires the knowledge of probability, whereas your classical bit string representation does not need that. Your direct representation of classical information does not need the probabilistic description. But sometimes what I do, what we create certain probability distribution of this 0 and 1, that what I transmit in a transmitting antenna or in some radar or some other applications, what is my market variable on that the uncertainty from data description, not the actual picture or the actual information representations. Okay. So to understand how the so there is like data representation is quantum itself is probabilistic. Then if you do measurement, if you measure this wave function on certain computational basis, that is also probabilistic, right? Probabilistic, because what information it is there, I cannot see it, right? Because it is in the quantum state. Once I measure it, I can tell, okay, this is out of 100 measurement, I am getting 0 this much time. Out of 100 measurement, I am getting 1 this much time. From that, I only know alpha and beta. That means measurement is probabilistic in nature. Also, when it passes through this information, suppose ket X passes through various quantum gates, right? You apply various quantum gates like U1, U2, U3. This all together makes a quantum circuit. So this information basically changes to some other state, say phi of X, right? And this phi of state, that is the evolved state. Now every U1, U2, U3, they have physical limitation, noise behavior due to coherence time and other stuff like coupling error. There are lots of errors in the picture we'll see later on. So that all together basically can do the bit string change. Suppose this is the bit string is 00001 and you get 00010. Suppose this is what you get. And all are say Ket, okay? Ket notation, quantum information. That means this particular and this particular qubit are basically contaminated by error, right? Contaminated by noise and produces an error, right? So to understand like the behavior of noise and mitigate the noise, we need to basically use the probability and statistical theory here. So let us come back with the basics. What is random variable? What is expectation value calculation? Right? And some other things. So in the notes that I shared, those who lacks the basic probability theory like union-based probability definition, conditional probability, Bayes theorem, the discrete random variable, continuous random variable, central limit theorem, every details is there. Let me just tell you the definition of random variable because the expectation calculation we already have seen beginning of this lecture. So I'm not repeating that part. And then we'll directly connect this phenomena with the quantum computing. Okay. Okay. So what is a random variable? So if there is an experiment and we do not have definite knowledge about the experimental outcome. So what outcome it can generate, I defined by a set some omega or something, right? And there is uncertainty in the output that it may, if it is a coin toss, it may be head or it may be tail, right? So if there is not a definite answer, okay, it is always, it will be head or it is always will be tail, or you can coin a die, there will be 6 faces of the die, 1, 2, 3, 4, 5, 6. So there is a, this is called a random trial or experimental outcome is not definite, right? In such situations, actually, when you have uncertainty in the outcome, right? So that is how you define the event, and this is called a sample space. Okay, so there are some engineering contest you need to start, sir. Contest or context? Okay, can you repeat y1, y2, y3? Where is y1, y2, y3? Okay, this part. So basically, when your information passes through various hardware blocks, right? So typically, if it is a engineering system, right? So if it is a receiver, there are many like modulator, mixture, filter, like low noise filtering. There are many steps, and every steps can produce certain error, right? So altogether, information is always like interfering, and some uncertainty is there with the actual. So actual information, if it is X, and then some uncertainty W is adding to the information Y, right? So if there are many such hardware blocks, you are certain to prone to various noise and errors. Okay. Hmm. Which one is more noisy, whether classical or quantum? Quantum is more noisy. But we are trying to go towards the fault tolerant region by mitigating various sources of errors with various hardware development technology and algorithmic approach. A tip plate, sample space, Borel field, probability functions. Was this asking this question? This question is not clear. I'm a mechanical engineer and all this mathematics going on top of me. So these are very basic mathematics like probability theory. Okay. So I provided the detailed note. Professor Pillai sir will share. Please repeat it. If you do not understand, don't worry. So there will be like in QT1, 2, 3, there will be repetition, like especially QT-03, there is totally complete 7, 8 lectures on probability theory. Maybe somebody will cover in details, don't worry. And similarly on linear algebra also there are 7, 8 lectures, more advanced lectures will be there. Okay. Now Now the question is, what is random variable, right? Now, many places when you ask this question, what is random variable, people say it's a variable which is random, or like, okay, first of all, random variable is not at all a variable. Okay, it's a function, right? And these functions maps any abstract phenomena to the real plane. Okay, abstraction to real axis. Okay, this is the purpose of these functions. That means whatever mathematical, whatever way we have defined the sample space, right? H and head and tail, but it doesn't mean any mathematical sense of this H and T, what is head, what is tail, and all mathematically or quantitatively. That's why if I can design a functions that I say, okay, head equals to say 0 and tail equals to say 1, right? Now I define the same sample space in 0 and 1. Now it makes a real numbers, right? Similarly, 1, 2, or -1, +1. So that way, basically, it converts the entire abstract definition of the phenomena, uncertainty phenomena, to the real axis, like the real numbers, right? So that's the purpose of the random variable. Now it may be continuous or it may be discrete. So continuous example, I'm giving you the example without mathematical details. So it's the temperature of a day, right? Say, for example, in the morning, you can see, suppose this is your 6 a.m. and suppose your 6 p.m., right? So you see in the morning, the temperature is quite less. The noon hour is temperature is bit higher, and the afternoon there is again the temperature is less. Say this is like 32 degrees centigrade, and this is say 24 degrees centigrade, right? Something like this in some city, right? That means there is a certain variation of the temperature over a day, right? So then particularly we can see like how actually the temperature is varying over the day is a continuous process, right? Continuously it is varying, but we are measuring it in certain time period like 6 a.m., 10 a.m., 12 a.m. So these are like any particular time when you see what is the temperature, those are the discrete values of temperature, right? So then we collect all those values, right? And say, okay, it is 24, 25, 26, and so on to 32, and keep it in a vector form, right? And we called it as a random variable in the vectorized form, right? In this way. Similarly, if it is a like continuous variable, you cannot write in this discrete form. So you define the temperature function as a f of x or f of t, for example, in the time, like time versus the temperature, or t or t, t of t, if capital T is the temperature, which is a function of time, here temperature of a day as a function of daytime here, right? T of t. So T of t is right now is a function on t is basically a continuous random variable x, right? Now, if I say what is the average temperature, right? So average temperature or the expected temperature is integration of T of t dt between 6 a.m. to 6 p.m. This is your expected temperature, expected T. In if I say you what is the what is the for the discrete random variable x, what is the temperature, expected temperature? So you take all these things and take the average of this, like sum of all this, and how many basically points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 you divide it by 10 and add all the temperature, you will be getting the average temperature. So in simply way, if you know the probability of each particular terms, and you have the probability mass functions P of x, that is how many times 24 is repeated, 25 is repeated, 26 is repeated, and you get all the entire spectrum, and that is called the probability mass function. Basically, if you know that, right, then your expected temperature will be summation of x, means this vector, times the probability mass function P of x for all x, right, for all such points. So it will give you all the probability. So that's simply probability mass function. And if you know the probability density function, you can do integration, right? So basically it is t tt dt. Okay, there will be another t, I missed it, right? So like if it is, I mean, so actually it is e of x equals to integration x fx dx, right? If x is your continuous random variable, fx is the probability density function, and dx, okay, for all such x. So I'm just giving you an overview, not the detailed, because if I want to cover detailed of these things, it will take at least 7, 8 classes for much more elaborations, because most of the audience are professors, they already know these topics. Still, I shared the detailed note, right? So there is a thing like this central limit theorem. So if you have a sequence of random variables like x1, x2, x3, xn, and they are basically independent, and they are identically distributed. Identically distributed, the meaning of identically distributed is the probability density is almost same, right? And independent means it does not, the impact on the second random variable does not depend on the impact of the first random variable. The uncertainty that is causing x3 is not dependent on x2 and so on. That means they are independent random variable, right? So all of them experience independent uncertainty, right? In simple words. Then if that is the case, and if there are, if n tends to infinity, that means there is a large such random variable, right? If that is the case, then the sample mean or the expectation for the these things. So there is two things. One is called the sample and one is called population, right? So population means if you can consider it's a entire country, right? Samples means you pick up a city and calculate certain things, right? So city versus country, something like that. Okay. So total populations is a bigger number, a sample is a small number. And I'm not just describing the entire thing, but we are targeting a sample, small part of the population. And mean of that is 1 by n and summation of all individual, right? That is the mean of the samples. Individual sample you add and divided by the number of samples. That is the average sample or the sample mean. It approaches normal distribution. So there are like distribution of the random variable, like there are probability density function for continuous random variable, probability mass function. We will see this from quantum measurement outcome, probability mass function, right? And there is called a CDF, like the cumulative distribution function, right? There are three things I provided in the note. Don't worry, you can have a look. But in general, if we see a sample mean, means we are considering like probability mass function here. So sample mean that approaches to the normal distribution or the Gaussian distribution with zero mean and one variance, right? Or standard deviation 1. So Gn equals to xn minus mu mean divided by sigma by root n. Sigma is the standard deviation. It approaches to normal distribution. So this is called the central limit theorem. What it tells you that there is uncertainty, right? So you repeat a process for first time, you repeat a process for second time, you repeat a process for third time. Every time you get the accumulated random variable, and all together this is x1, x2, x3, and so on. I cannot comment the individual distribution of these things, how it looks like. But if I take many such samples, like infinity or very large number of samples, I can see the mean of this total samples will look like this. Like the temperature of a day, I have shown it, something like that, right? So this is as per syllabus, like central limit theorem, and I don't know whether central limit theorem is applicable to quantum computing or which context. I don't know. I don't have a clear picture on that. But this is important in statistical analysis, right? Okay. So we have roughly 29 minutes, and so I'm not repeating all these coin toss or head and tail things, but there are enormous examples to do that. Now let me give you some questions in this context. Maybe you can. Suppose Suppose we run a quantum circuit. We run a quantum circuit. Basically, quantum circuit is the circuit representation of an algorithm, right? Suppose we run a quantum circuit 1000 times, right? And measure Gate1 in 520 trials, right? So the maximum likelihood to estimate the probability P, if I represent as alpha times Gate0 plus beta times Gate1, right? And the probability is beta square, right? So can anyone tell me which kind of distribution it is? Which distribution this experiment follows, right? Answer we all know. Answer is probability is basically 520 by 1000. 0.52. You do not need to calculate anything. Just tell me which distribution it is. Perfect. This is binomial distribution, right? So the formula of binomial distribution. Now, immediately you know that quantum measurement on computational basis gives the binomial distribution in k p to the power k 1 minus p to the. This is the probability of success. Probability of 1 minus success, that is probability of failure whole to the power n minus k, right? This is the probability mass function for binomial distribution, right? Right. I'm giving you a hypothetical experiment, right? Suppose you create a photonic channel, fiber optical channel, right? And instead of giving definition and problem, I'm just giving you certain just flavor how it is related, and you just send, say, n number of photons in the fiber optical channel. Suppose this is, say, Delhi, and government of India invested, say, few lakhs crore to design a fiber optical channel. And suppose this is Mumbai, suppose this is Bangalore, this is Chennai, and there are other cities, right? And in every city, suppose there are many optical devices like splitter, many other things, and you measure number of photons, some number of photons here, some number of photons here, some number of photons here, right? So on an average, how many photons can I get? Say if some photons are sent in 10.10 AM, right? Actually, I should calculate in microsecond or femtosecond, but just for simplicity, suppose it takes some time to reach from Delhi to Bangalore or Delhi to some city, Chennai, right? Suppose it takes some time. And out of this n number of photons, if I get n1 number of photons in some other time, say for example 10 at 11 AM, 1 minute it takes, for example, right? So in a particular given time, what is the rate of photon it goes through this channel, this particular channel, right? There are other channels as well. So which distribution it can follow? Any question? Anyone? Can anyone tell? The rate of photon that passing through this Bangalore channel, Delhi to Bangalore channel. Exactly, Poisson distributions, right? So now you know that all your knowledge of probability theory will help you, like to design certain quantum splitter and certain things. So which device you should put, like at what speed you should get the data, or at how many number of photons that will, because photon will give you the quantum state, Gate0 and Gate1, right? So like how you transfer the information at which rate and all, you need to have some understanding of the Poisson distribution, right? So now that is related here, right? There is also something called the quantum channel. I'm not giving any details here, but just telling you that suppose I have a bit string, say 000, right? But I want to receive 0, 1, 0. right? Can anyone tell me what is the quantum channel here? So there is a bit flip, you can see, right? So for the first bit, there is nothing, means identity matrix. Second, third, there is no change, there is identity matrix. What is this quantum channel? This one. So many answers. This is X, simply X, Pauli X gate, right? Because Pauli X does this 0 to 1, right? X, if you apply to 0, you'll get 1. X, if you apply to 1, you'll get 0. That's why Pauli X is also known as bit flip channel, quantum channel. It's a noisy channel. That means if you get some information like this way, you can model a channel using the Pauli X gates. I mean, there you won't have a like 2-qubit, 3-qubit thing. Picture is much complicated, but in simply I am saying just if there is a circuit, 3 qubits are there, 0, 0, 0, but there is a circuit and you get 0, 1, 0, right? And you do nothing here. Suppose you do nothing here, simply measurement, and you are getting an error in the second qubit, right? That means there is a bit flip here, equivalent to Pauli X channel, right? First and last should not change means identity. If you multiply anything with the identity matrix, like 1, 0, 0, 1, there is nothing changed, right? Multiplying 1 with any number, you get the same number. Similarly, multiplying identity matrix to a quantum state, you get the same quantum state. Right? As simple as it is, right? So there is channel like something called a depolarization channel. There is phase damping channel. Many other channels are there, and these are highly associated with the probability theory, that 2/3 of the probability I should pass to that way, and 1/3 of the probability I should pass this way. So depolarizing channel looks like this. I'm not giving the details at all here. Will come sometimes later. Probability of error, 1 minus probability of error times rho. It's a density matrix basically. I'm not defining it today. And probability of error by 3 x rho x plus y rho y. It's basically a quantum state in matrix form. Okay, we'll see later. G rho g. So this is another basically some error model for quantum channel. So there are lots of various quantum channel model and all using the probability theory. You can model them. You can calculate the expectation value, certain other parameters and all to those settings, right? Similarly, you can think how to mitigate those errors and all based on the expected result. So these are some of the things, right? And okay, binomial distribution, normal distribution. Let me find 1, 2, 3 exercise questions because we have some more time. Maybe we can utilize that. Just allow me some time. Okay, another experimental situations. Let me shortcut to identity distribution or any prerequisite, please. I'll recommend to go through all the basics of probability theory, especially all the discrete distribution, all the continuous distribution, basic concept of simply the mean expectation calculations, variance. Higher order statistics is not needed, but some amount of knowledge in likelihood function, the log likelihood functions, those things definitely helps, especially if you are interested much in the measurement methods such as the tomography and all in quantum computing. You should have some knowledge in the estimation theory, right? So such as the log likelihood function, Bayesian inference, those things. But if you are stick to simple like rank 1 measurement, like simple Z basis measurement, there is nothing new. Simple histogram probability mass functions, binomial distribution, all the discrete distribution will help you, right? So okay, let me give you some scenario maybe for hypothesis testing situation, right? Instead of defining things and all, let me give you a quantum computing scenario. The question is, this is related to type 1 error, type 2 error, these things, okay? A quantum computer is designed such that, the question is, a quantum computer, let me write it. A quantum computer is designed such that its final measurement on a specific qubit should ideally yield Z0 with probability equals to 0.95. Suppose I want to design a quantum computer such that I should get ideally all the Z0 with probability 0.95 and probability of, this is probability of 0, okay? Probability of 0.95 and probability of getting the state 1, Ket1 is basically 0.05 is the probability of Ket1, right? Suppose I have to design this and you are running a classical simulation algorithms to do this, right? Suppose you are running a classical simulation algorithm to design this quantum computer or quantum algorithm, right? So if your simulation generates a uniform random number, situation 1, if your simulation generates a uniform random number between 0 and 1, uniform random number between 0 and 1, right? How would you use this to simulate a probabilistic outcome of quantum measurement? First question, simulate probabilistic outcome. Second is, if you simulate the measurement 50 times, now if you simulate this experiment, simulate it for 50 times, what is the expected number of times you would get? What is the expected number of times you would get the outcome 0? So first of all, to simulate a discrete probabilistic outcome with 0 and 1, right, with probability P of 0, probability of P of 0 equals to 0.95 and probability of 1 equals to 0.05. So we have to use, of course, uniform distributions, right? Uniform distribution, because we are using simple normal computer to simulate it, this quantum experiment, right? Simulation. Now basically, can anyone calculate this if possible? Second part. So first part is like you create a uniform distributions and you can do this. This is fine. Second part, that is, if you simulate it for 50 times, what is the expected number of times you would get the outcome 0? Exactly. So we just simply need to multiply 50 into 0.95. 47.7, right? Now, let me give one last question here. Suppose a quantum hardware engineer is characterizing the performance of a quantum gate. And question number 2. Suppose there is a quantum hardware engineer who is characterizing the performance of a quantum gate. They perform experiments with varying number of operations x and measure the average fidelity y of the quantum state, and they obtain the following data. Suppose this is the data sets. And this is the number of operations x and average fidelity say y. So this is fidelity and this is the number of operations. X is the number of operations, right? So 1, 2, 3, 4, 5. 5 times we will operate and we get the quantum experimental result fidelity. Yesterday we defined that is the closeness of two quantum state, right? 0.99, 0.98, 0.96, 0.95, and 0.93. Right? So calculate the expectation of like the expected fidelity first. These are very basic questions. Yes, what is the expected fidelity? Right? And then can you formulate a regression equations between these x and y? Right? That will be a bit difficult. Okay, leave it. It will take some time, but this one and uncertainty in delta y also you can calculate. Variance of y, maybe. So very basic questions. Someone is giving 0.962. Let me check some of the other answers. So very easy question. Okay, let me give one question from some distribution. Find one question. Cost function. Okay, this is a good question. Okay, suppose somebody gives you a probability density function as this. F of x equals to 0.5 e to the power minus 0.05x, right? For x greater than equals to 0 or it is equals to 0, right? For x less than 0. If this is a PDF, some PDF is provided, right? Can somebody tell it's a valid quantum state or not? Can it be a valid quantum state or not? Although all the examination, like the MCQ questions will not be this type, that will be much easier with options. But suppose it's a true false question, right? This answer is correct, 0.962 or 95, this is correct. Those who are getting very close result, that's correct. Now this question. Okay, let's see. I'm seeing varying types of like answers. Yes, false. Okay, let's see. Let's see for 2-3 minutes whether it's a valid quantum state or not. Those who are answering yes, can you just explain like comma, like in one sentence? Yeah, so you just need to integrate this over 0 to like 0 to infinity, and you will get the answer. So if the integration equals to 1, then it will uh, give you the valid quantum state or not, right? So those who are saying true or correct answer, they are correct. Actually, you just simply need to integrate it over 0 to infinity fx dx, right? Now, one last question. Expectation value in quantum computing, right? So we need to define this as well. Expectation calculation. So in quantum mechanics, the mean of measurements, measurement is known as the expectation value for the observable, for an observable A, right? Often we represent by a Hermitian operator, because to get a real quantity in physics, the expectation value for a quantum state, get psi is given by, it is written as digital board sometimes create lots of issues. Yeah. It is written as expectation of A, or more better way, it is written as this way, like psi A psi. This is the representation expectation calculations or the mean calculations in quantum mechanics. So if you have given an operator A, then the expectation value of the operator for the of the quantum state psi given the operator A is psi A psi. Okay. So so basically this is a bra vector, like row vector, the matrix times the column vector, right? So for a single qubit, the observable for measuring g axis or z axis is the Pauli G operator, sigma G operator, uh, given by sigma G equals to 1, 0, 0, minus 1. The eigenvalues, because if you apply G vector on Ket0, you get Ket0 with eigenvalue equals to 1. If you apply G on the state 1, you will get minus 1 times Ket1, means eigenvalue equals to minus 1, right? So let's find the expectation value. Can somebody tell what is the expectation value of this? Right. So suppose let's take Ket psi equals to, the state is alpha Ket0 plus beta Ket1. This is my state, right? Now calculate this one, right? So I'm just writing the equation for simplicity. This is alpha star this plus beta star this sigma z times alpha Ket0 plus beta Ket1. This is equals to sigma, the expectation, sigma z. Right? Now calculate and tell me the answer. What will be the answer for this state? So what will be the value for this? No, there will be no one, right? The answer will be in terms of alpha and beta. Okay. You can check. You just simply multiply this vector times a matrix times a vector. That's all. Just a simply calculations. Even you do not, this is so easy actually. Some of the product will cancel each other, like 1 times 0 or 0 times 1. In fact, you can apply the this sigma z times 0 equals to 0. This formula also you can apply. Some of the places you will see this kind of situations. Right. I just applied the expectation calculation formula. Just defined it here, right? So here your age equals to sigma z. That is the z operator, Pauli z operator, right? 1 minus 1, 0, 0, right? And your psi is basically alpha ket 0, beta ket 1. You just need to calculate this and tell me the answer. In fact, you can calculate both the mean, like expectation, that is this one, and you can also calculate the variance of sigma z, both the value, because this part is related with uncertainty principle. Right. Just have a try and I got 2 correct answer. Let's see. Last 2 answers are correct. Alpha square. So the answers, let's try it. Suppose in your exam, the options are alpha square plus beta square, alpha square minus beta square, alpha beta minus beta alpha, answer 0. These 4 are the options A, B, C, D. Okay, so check it. Yeah, I am giving 1 minute time so that everyone can try it. Right? Yeah, the correct answer will be B. That is the basically alpha square minus beta square, right? And I am giving last definitions. So this is my last class in this course. That is required, and that is called the commutation operator. Although in notes I have given commutation operation. The definition of commutation operation is that if A and B are 2 quantum operator or any matrix, right? Then this is equals to AB minus BA. If the result A comma B, this commutation equals to 0, we say that operator A and B commute each other, right? So for example, all the Pauli gates, sigma Z, sigma Y, sigma X, they are commutating operator, okay? If they do not commute, that means A comma B not equals to 0, we say A does not commute with B, does not commute with B. And there are lots of complication to design with the operator, the quantum circuit for the operator which does not commute with each other, does not commute with B, right? For example, if you design an operator for the position operator, say X hat, and yesterday we have seen, like 2 days back, the momentum operator, you compute this value, that is X hat, P hat time on the wave function psi X, you will see that X hat that is applied P hat first on psi of X minus P hat applied later on X hat psi of X basically, right? So it's that way you can do it, like first and second part, like AB minus BA that way. So you'll see that this is in fact not 0. In fact, it is equals to H, some new or some term will come here, right? Some term will come here. So some I H bar or some terms will come here, right? So that's why we'll say that if it is not 0, so there is uncertainty between these 2 operators, positions of the wave function in that 2 operator, positions and momentum, right? It may be your time and frequency operator. If you apply on the wave function psi X, you will see this is also not equals to 0. That means if you get some very good understanding of the wave functions or representation of the wave function in time domain, definitely there is high uncertainty in the frequency domain or vice versa. Yeah, thanks. With this, I conclude the sessions now today. I I congratulate every one of you for attending this course, and I thank everyone for your kind attention. Because this Thursday evening, I'm seeing 500 participants, so that's a great number. Thanks. Sir, you waited a long time. Thank you so much, because your time is valuable, but still you are sitting here. So this is a great honor for me as well, sir.
Right, right. No, no, yeah. In fact, my wife has also joined today on YouTube
Great.
because she's a maths teacher. So she wanted to listen to the probability. And I said that his approach to subject is very interesting. So you listen. So she's there on YouTube. So thank you so much, participants. And I think only thank yous are there. No questions are there. So I think it was a wonderful lecture. And if you have any questions, please write. Otherwise, we are on time. We will conclude because we started on time. And thank you so much, participants. You're all 500 of you are very regular and sincere. I am happy that you are continuing. And I get a report that many of you are also watching on YouTube. About 500 people I have watched all the videos. So 1, 2, 3 videos have been watched by more than 500 people. So that's also a very good, what do you say, a very good indication that you are revising. And I think in Canvas also you are logging in and watching the videos. I think some people timings may be an issue, but then yeah. So thank you so much for doing that. And see, please understand that you have not paid the fee. All those who are here and your friends, please remind them that certificate will be issued only for those who pay the fee. Lectures are free, and of course you can take the exams also. But I'm very happy to note that Canvas, about 800 people have registered on Canvas and they've logged in. So I will know when they write the exam. So many of you may want to write the exam because you are attending the lectures during your free time, which is not matching with the attendance. I think I understand that also. So we'll exactly know how many of you take the quiz, right? So let's hope that, yeah. So sir is answering the questions. Book that is there, Popolis is the author, so you can look at that, right? It's a good book. Yeah. So this is what I wanted to explain to you. This Saturday we will have a quiz. So Mustafizur sir's content will be mostly covered there, right? And then tomorrow Richa madam will also take the class and on electromagnetics. That will also be part of the syllabus. You don't have to take it tomorrow immediately after the class. If somebody is prepared, you can take it. Saturday syllabus will not be covered in the quiz. Monday to Friday syllabus, the 5 days lectures series, that content will be covered. The quiz will be open till Monday midnight. So Saturday evening you can prepare and write. Sunday you can prepare and write. Saturday, Sunday you can prepare and you can write on the Monday evening, Monday midnight till you should have start by 11 o'clock. Otherwise it will be difficult. And then please be sincere. You are all teachers, so I think you will not copy from anywhere, and you will try to be sincere. Assess yourself, right? There is no award. There is only, okay, you will get excellent or very good, no problem. That's not a big issue as long as the certificate is there. And if you complete more courses, maybe APSHE may give you a kind of a separate honor for that. And then you will be eligible to be a train the trainer. So that is more important. Please look at that part, and you can try to look at, right? So anything else you can write to me. I will share 4 WhatsApp numbers, myself, Dr. Maipal, Mr. Deepesh, and Mr. Ramesh. So 4 of them will be available for any clarifications, maybe tomorrow evening we'll do a demo on Canvas, how to join Canvas, so that because on Saturday you will start taking the exam, or maybe on Saturday only we'll do. Saturday will be little relaxed for all of you. So tomorrow you attend the lectures, and Saturday we'll do that, right? Thank you so much, and we will meet tomorrow. Tomorrow, Dr. Richa Goyal will be there. So we'll thank Dr. Mustafizur for giving us a wonderful introduction to quantum computing. Informally, a lot of quantum computing has been explained, and also mathematics and statistics has been covered. And more detailed content will be covered in QT-00, 03, and so on. And in quantum computation, which comes in quantum 05, again things will be repeated. So don't worry. We are only giving a cursory introduction in this course. We are revising whatever you are. So thank you so much, Dr. Mustafizur, for your valuable time. 10 hours you already spent with us. Thank you so much. And we'll continue to interact. And then sir will be taking next sessions in QT-00, 02 also and 03 and so on. So as we go into those contents, you will really enjoy. Right. Thank you so much. And thank you all of you. And you are able to see the response. So I think it is always like that whenever Dr. Mustafizur completes his class, right? Thank you so much. So we'll wind up here and we will meet tomorrow at 3 o'clock.